Welcome, everybody. This is Mr. Olson, aka the Bob Ross of science. And today we're going to be drawing some diagrams showing environments of mineral formation. So here we are for starters. Yesterday we talked about how minerals are solids. They're naturally formed. They have an atomic formula, a chemical formula that shows how the atoms are connected to each other. Let's see, they also have to have a crystalline structure. So we did a little activity yesterday showing how atoms will find their bonding partner and start to form a crystal structure. So this is where we'll continue today. First off, minerals form when dissolved elements bond together. The elements have to be dissolved so they can move around and find their bonding partners. They have to find another atom that they want to bond with. When atoms do bond together, they'll form a three-dimensional pattern that's called a crystal structure. For example, halite, which is also known as rock salt, has the formula NaCl, sodium chloride. One sodium atom bonds onto one chlorine atom. And in our diagram, we're going to use orange for sodium and green for chlorine. So we started yesterday. We can see that here's a sodium atom that bonded onto a chlorine and some other atoms that were floating around in the solution said, hey, I want to be part of your crystal. So they started to join in. And they will form a repeating pattern. It goes sodium, chlorine, sodium, chlorine. And then the next row down would be kind of just the opposite of that, chlorine, sodium, chlorine, sodium. And so we end up with what's called a crystal structure. And we tried to make ours three-dimensional by showing that they would bond off in all directions with that repeating pattern. These extra atoms that are here could add to the crystal structure by bonding into place. And this is what's kind of cool. Once you have a very tiny crystal, it's called a seed crystal. The seed crystal is going to establish the pattern. And then any extra elements that bond in are going to follow that pattern. So the longer that these elements stay dissolved in a liquid, the bigger the crystals can grow. So I'm going to pause my recording for a minute and give people time to catch up to that part in their diagram, and then we'll continue. And we're back. So now that we know a little bit about, in general, how minerals form, with atoms being in kind of a liquid, dissolved into a liquid and then moving around to find their perfect bonding partner, we're going to go ahead and check out some specific environments on Earth where you might see this happening. So first off, I would like to check out a spot in New Mexico. So when I was a kid, my dad used to live in a town called Newcomb, New Mexico. Newcomb, New Mexico. Way up here in the Four Corners region. It's definitely in the desert, way in the middle of the desert. I mean, look, it's just like all desert. There's not much in Newcomb, New Mexico. There's a middle school, or there's like an elementary over here, and there's a high school up here. They do have a pretty sweet football field, the Skyhawks. And then this is like teacher housing over here.
Teacher?
Yeah, teacher housing. This is the Navajo Nation, and so this is tribal housing over here, and then like the tribal like council house. But there's not much in Newcomb, New Mexico. I took a trip there on spring break during college with one of my friends, and we found a cool little dog. It was a stray dog, and we decided that we would adopt him. My friend said, I need a dog. I'm going to adopt him. So we took this dog. And it was a desert dog. He was super nice. And we started to drive back to Minnesota. And as we were driving, we stopped high in the mountains, like north of, I'm trying to think where we came out of. I was going to say maybe like Durango, Colorado. We went over this mountain pass, and it was deep, deep snow. And I was kind of shocked because, I was used to New Mexico being just like open desert. I didn't realize that there was, parts of the Southwest that are really mountainous and rocky and could have snow. We took this dog out for a bathroom break, and when he jumped out of the car and his feet hit the snow, that was the first time he'd ever touched snow. He tried to lift up all 4 of his feet at once. It was kind of funny. And this is why I think it shocked that dog so much. In the desert, sometimes you have this stuff forming. This is a spot that's called a playa. And playa is a Spanish word for beach, but it also is like a really shallow lake pond situation in the desert that eventually dries up. So, what do you think all this white stuff is here? What do you think it is, Maya? Yeah, it's sort of like baking soda actually, but it's like salty mineral crystals. And if we look in the background, we can see that it's still maybe kind of damp back there. So this is an area where all these minerals were dissolved in the water, and it dried up. The water evaporated, leaving the crystals there. And people call this desert snow. Desert snow. It's not really snow. It's crusty minerals. But I think that cute little dog was used to walking around on desert snow and wasn't ready for real snow. So we're going to try to draw that situation with the next part of our diagram. We're going to try to draw a desert playa. So here we go. So draw with me as we go. First off, we're going to define the landscape. I would like to have kind of a hill over here that sort of drops down here, and then like a third little spot that's still going to be full of water. And since this is the desert, we need to set the scene with a nice little cactus over here. Ooh. Little cactus in there. A little happy little. Oh no, I broke my pencil. It's all good. Sometimes these cacti in the desert will have a little flower that blooms off the tip of the arm. This would be like a saguaro cactus. A really good spelling word, saguaro. There you go. I'm going to put a little flower right there. And to make it look all cactus-rific, we need to add some little spines. And I'm going to go ahead and shade it in. Ooh, this is looking sweet. Don't you feel that you've been transported to a magical land far away? No? I do. All right, wonderful. So, down the hill, let's have this playa, this little shallow pond. We're going to make it kind of right in here. And we want to show that there are minerals dissolved in there. Now, in real life, we saw that desert snow. It's kind of white, but I think for our diagram, I'm going to do red just so you can see them easier. And think about this. In the desert, it's pretty hot. I mean, we visited my uncle once in Las Vegas on the 4th of July. It was 121 degrees. I couldn't believe it. It gets really hot. So the sun's beating down. Oh, yeah. I'm going to throw the sun in here quick. The sun's beating down. Got a lot of radiation. There's not a lot of clouds to block the sun's energy, so the sun's very powerful in the desert. And as a result, we're going to see that the water starts to evaporate. And although the water can evaporate, the minerals can't. Those elements are left behind in the solution. So these dissolved elements will form crystals as the water evaporates. We're going to add that caption. These dissolved elements will form crystals. as water evaporates. So up here on this little bench that we made, this little higher part of land, let's say that the water used to be higher, right? And let's show some minerals crystallized here. I'm going to just draw some little blade-like crystals. Again, in real life, these maybe would be white and just kind of crusty little baking soda-like crystals. But we'll make them look red so we can connect them to the minerals that we drew in the water. All right. So that's a little patch of crystals. And in general, we can classify that type of mineral as an evaporite. Okay, so let's write that here. These minerals are called evaporites. These minerals are called, and this is like a general name for minerals that form this way, evaporites. A lot of minerals, their name will end with ITE. For example, there's even a mineral called morganite. It's like a pink gemstone. Azurite is a blue one. Malachite is one. So many minerals end with ITE. Halite would be salt that we drew at the start. All right, so what do you think of our first little scene? To make sense how these minerals would form? Yeah. The water can evaporate, but the minerals can't. And so over time, that solution would get more and more concentrated with minerals, and eventually they would start to form crystals. You could try something like this at home if you wanted to dissolve some salt in water and then pour it into a shallow dish and let the water evaporate. Over time, you would grow crystals. And the crystals you grew would be as big as they can get in the amount of time they have. So if you kind of like let it slowly evaporate, you should be able to grow some pretty nice big crystals. You guys ready to move on to the next one? My class needs a little bit of time, so I'm going to pause my screencast again. And we're back. All right, for our next one, the next environment we're going to investigate, we're going to check out a situation kind of like you would see, for example, where the Mississippi River dumps into the Gulf of Mexico, or really where any river flows into the ocean. One thing we might notice if we take a look at here, the continent of North America, do you notice that there's like this shallow water and a weird kind of lighter colored area sticking out from the edge of the continent? Yeah. So that's called the continental shelf. The ocean water is shallower, and we're going to see that there's certain types of minerals that form along the continental margins. And you would see if we looked out here that many of the Earth's continents have a fairly large continental margin. Some of them don't have as much of a continental shelf, but we're going to check out kind of this scenario right here. What's going on as a river starts to dump into an ocean. So here we go. Back side of the diagram. All right. So this is going to start looking kind of similar to our first one. We're going to draw a brown line. This is going to be kind of like the riverbed. Then it's going to go into a shallow ocean area here. And then off on the side, it's going to drop off into deep ocean. We want to give ourselves a little bit of room at the top where we can write some caption space in here. But here's our river, and then it's coming out into the ocean. And I'm going to make my ocean look pretty sweet. with some deeper, darker colors over here. Some blues and some purples. All right, we've set the scene. So, when rivers flow across the land and when rain falls and runs across the land, it's going to dissolve a lot of materials and carry them with. So, the river would be carrying a load of dissolved minerals. So, we're going to draw those in here. And when the river dumps into the ocean, we're going to have all of these minerals that got dissolved from the land getting carried into the ocean. So we'll put a caption on the top. Rivers carry dissolved elements into the ocean. And of course, the ocean covers a large percentage of the globe, somewhere around 70%. And the sun beats down on that all day, and we're going to have water evaporating from the surface of the ocean too. So let's show that over here. Water evaporates. So water from the ocean evaporating into the atmosphere. When it does, of course, all the minerals are left behind, even the salt. So this is how our ocean can come back as fresh water. When the water evaporates, it leaves the salts behind, and fresh water goes up into the atmosphere, becomes clouds, and eventually rains back down. All right, so over time, if water can leave, but minerals keep getting dumped in, or elements keep getting dumped in, again, we're going to see like a concentrated batch of minerals here. Over time, this is going to become more and more concentrated with dissolved stuff. And eventually, it's going to start to form crystals. We're going to add one more big caption over here and then do a little bit more drawing. In the shallow oceans, along continental margins, massive layers of limestone are built from dissolved minerals. All right, so in the shallow oceans along continental margins, massive layers of limestone are built from dissolved minerals. Now, in geology, when we draw rocks, we have symbols that represent different types of rock. And the symbol for limestone is just like the brick wall over here. It's even the same color usually, kind of a tan buff color, and we draw it as bricks. The reason we draw limestone as bricks is because it can build up layer upon layer, hundreds of feet thick of limestone. And that's because all those dissolved minerals are getting concentrated and eventually crystallizing into really thick, massive blocks. So there's our limestone. Limestone's cool also because since it forms in the ocean, a lot of times it will have fossils in it. It'll have the remains of living things. So I'm going to draw a little fossil. I'll start with a spiral. And then I will just bring it in so we have a cool little snail shell, seashell type of situation. I've got some limestone I found in Montana that's got these, they're called gastropods, little shelled creatures in there. And here's an interesting fact too. The animals that live in the ocean that have shells, they actually create their shells by filtering some of these dissolved minerals out of the water, and then they can secrete the material that they use to build their shell. So they build their shells using these dissolved minerals. How's your diagram looking? Looking good?
Amazing.
Okay. So I want to check out a spot. We'll come back to this in class in a minute so you guys can continue drawing. But I want to show you a spot where you would find lots of this limestone. Florida. The panhandle of Florida here is pretty much all built of limestone. And that's kind of a bad thing because limestone is easily dissolved by even rainwater, which is a little bit acidic. So what we see here and what you might think are just a bunch of lakes, kind of like around Alexandria, these are actually sinkholes. So it's kind of like a cave that formed underground when the limestone dissolved, but then the cave collapsed. And a sinkhole is really dangerous. Check this out. Here's a few pictures of some sinkholes in Florida. Can you imagine if all of a sudden part of your house just fell into the ground? And that's because that limestone underground is dissolving. And eventually it'll collapse. And you don't even, I mean, there's no way to really predict it, right? Uh-huh. Well, another problem with Florida, too, is that when there's like a storm surge, for example, in a hurricane, a lot of these are connected to the ocean. So ocean water can actually flow through the ground and up through these and kind of flood the ground. It's really it's really a bad situation. And as we take a look at the potential sea level rise that we might see in the future, Florida is one spot that's really kind of susceptible to some of the effects of our changing climate. All right, we're going to pause and let people catch up with their diagram. All right, we're going to check out one more environment where minerals could form. This one's kind of interesting. Since we're in the ocean here, this will make sense. Along the ocean floor, there are structures called hydrothermal vents. And a hydrothermal vent is a spot where heated water from the ground comes out. And a lot of times it's carrying with it a ton of dissolved minerals because the water's super heated. In general, there are kind of two types of hydrothermal vents. One of them is generally called a white smoker because the gases that come out are kind of whitish. And another one's called a black smoker. So this one would be like a black smoker. And here's kind of a diagram that we're going to work from. If you check this out, inside the Earth, there is magma, sometimes fairly close to the surface. And look at the temperature on that magma, 1,200 degrees Celsius. Water is going to flow down into the Earth, and it's going to become superheated as it gets close to that magma. And since it's under pressure, you can force water to be hotter than its boiling point. When you put pressure on a fluid, you can raise it past its boiling point without it boiling. So in this case, the water that's coming out of our hydrothermal vent is 350 degrees Celsius. Wow.
Isn't Celsius like times 2 Fahrenheit?
So 100 Celsius is the temperature at which water boils. And so you think about this. This is like 3.5 times as hot as the boiling point of water. So when it comes out, it's carrying a ton of dissolved minerals, even metals. And if you look, as it starts to spread its plume through the ocean, it cools quickly. Now it's like 2 degrees Celsius, which is about 40 Fahrenheit. And those minerals are going to crystallize and start to fall out as particles. And you can see that you'll end up with a whole bunch of sediment that's very rich in metals deposited next to a hydrothermal vent. And when we talk about these metals, you could have really valuable stuff like gold, silver, platinum, like really valuable metals actually build the walls of the vent themselves, um, and could potentially be mined for their metals. Crazy. Also, there's special bacteria that will feed on the sulfur and some of the other chemicals that come out, and they create their own food chain, like deep in the ocean, far away from sunlight. There's thriving communities of strange organisms that live off of that material. So we're going to try to draw that, all right? All right, so bear with me here. Once again, we're going to start by drawing the landscape, and what this is going to be, we're going to go almost halfway down your last little panel. This will be the ocean floor. So we'll keep it kind of flat. And then over here, let's poke up a hydrothermal vent, so kind of a chimney-like structure. There's our hydrothermal vent. Let's label it. Hydrothermal vent. And I'm going to draw a plume of black. So it'll be a black smoker. So we'll have like a plume of black smoke coming out of it, spreading. Keep in mind, this is underwater, deep in the ocean. There's our black smoker. As the minerals that are dissolved in there start to chill, we're going to have them crystallizing and falling back out as a metal-rich sediment. So we'll make a little deposit here on the ocean floor. All right, cool. We'll add a caption in the corner. Deep inside the earth. Superheated water dissolves elements, even metals. When pressure is released, the minerals crystallize. All right, so just to set the scene here, I'm going to go ahead and shade a little blue around here so we know that we're underwater. If you were going to draw a fish on your diagram, you'd want to look up one of these really creepy deep sea fish, like the lanternfish. Oh, those things are so creepy. I know. All right. Now, let's get down into the ground a little bit. So we understand how the minerals are forming like as they come out, but let's see what's happening down inside the ground. What I want to show here is that the plumbing of this hydrothermal vent, so like the pipe that's bringing this hot fluid up, actually is going to connect deeper down, and it's going to be coming close down here to a body of magma. So let's have like a branching network of kind of cracks that water could move through. And then this is the coolest thing you're going to draw all day. We're going to draw a magma down here. We're going to draw a magma chamber. So let's label it first. Magma. All right, so I'm going to really shade mine in. I'm going to do like red on the edge. Then I'm going to bring in some orange. And I think we'll finish it off with a glowing yellow. That's cool, isn't it? See, I don't know about you, but I'm a visual learner, and to me it makes a lot more sense to kind of draw a diagram and construct your knowledge as you go. You can see it, and as you're drawing it, you're kind of putting the pieces together in your mind. I think, they say a picture's worth 1,000 words. It really is. This shows a lot. All right, now, so we have superheated water that's going to be moving through these channels underground. And like I said, sometimes that water will find a crack in the rock. So I'm going to draw over here like a little vein, like a crack in a rock that the water could kind of force its way up into. And since there's going to be a little bit less pressure inside that empty crack, the minerals will crystallize. So this would be a spot where you might have the mineral quartz crystallizing, and with quartz a lot of times is gold. So I'm going to color this one in and say it's a giant underground vein of gold. Man, that'd be sweet. Gold! Solid gold! Nice. I'd love to find something like that someday. Here's our superheated water with minerals dissolved into it. I'm using black just to kind of represent some of those dissolved minerals and things. Cool. Now there's one more thing I'd like to add here, or two more captions here quick. So over here, minerals form in veins in the rock. And then the other one that I want to take note of, you might have a mineral that's underground and there's so much heat and pressure on it that it changes. That's called metamorphism. It would metamorphose or change into a totally different mineral. And that can happen just from heat and pressure. So I'm going to add that over here and say also heat and pressure can change one mineral into another. And we're going to study that in great detail during our next unit. Yeah, for example, you could do carbon compressed into a diamond. Yep. That's a good one, Jack. All right. Well, take a look at your diagram. Are you proud of it?
Yes.
Is it sweet? Does it tell and show what's going on with minerals forming?
Yep.
Do you think that you'll have a good grasp on this content since we took time to kind of like make it happen in front of our eyes a little bit? Sweet. All right, well, thanks for drawing with me today. I'm going to sign off this live stream. People at home, we'll see you when you get back to school. Have a great day. Enjoy your weekend. Thanks for drawing with us.